So we're going to talk numbers with circuits today. So back to circuits. But before we do that, we have to change our pictures. If I were to draw a circuit, let's say, for example, rather than use my the picture I used before, I used a AA battery or AAA battery. Those are the ones that look like this, right? This terminal of the battery is the flat end is the negative and the nubby end is the positive. And let's say I had that going over here to a light bulb. Let's say here's my light bulb. There's that little metal screwy part on the bottom of the light bulb. And here's my, that's a terribly shaped light bulb. Let's say that that's the thing inside the light bulb, and there's my light bulb, and it's giving off light. Boom, right? We said that the light bulb is an example of something called a resistor, and the battery is our potential difference, or source of potential difference. But the battery is not the only thing that could be the source of potential difference. What happens if I plug into the wall? When you plug into the wall, you actually get a potential difference of 120 volts, between the two prongs of the wall. That's why all plugs have two prongs in them. Well, we'll talk about the third prong a little bit later, right? And here, the thing that is taking the electrical energy and turning it into some other form, it might not be a light bulb, it might be a TV, it might be this, but we know that this thing is called a resistor. So rather than having symbols for scientists and engineers and contractors to talk to each other that look like the things, what we've done is we've created a series of symbols. So a source of potential difference, specifically a battery or something that is a constant potential difference, has the following symbol. It looks like a long and a short little plate like that. So it almost looks like a parallel plate capacitor, but not. The long plate is the positive terminal, the short plate is the negative terminal. Now that might also look like this, long, short, boom. And then we just label the outermost negative and positive, or maybe even long, short, long, short, long, short. There we go, positive and negative. As long as it's a long and a short. Well, why is that? Well, historically, where this came from was the work of someone named Alessandro Volta, an Italian scientist. And what he found is that if you put a copper plate and a zinc plate on top of one another in an acid bath and connected wires between the copper and the plate and the zinc plate, that you got a flow of electricity or electrical current. I am vastly oversimplifying Volta's work, but there it is. And so this symbol is to represent Volta's original, what he called voltaic pile. And why is one long, one short? Well, very simply, he had more copper than zinc. So he had big plates of copper and small plates of zinc. And so that's what was going, actually no, opposite way, big plates of zinc, small plates of copper, So that's what's going on there. So what do you think is the difference between these? Well, it just would be in a circuit, this one would have a greater voltage or potential difference than that one. So if you have an electrical device, sometimes it needs, say, like 4 AAA batteries. Each AAA battery provides 1.5 volts. This might be something that's suggesting that you need 3 batteries, 2 batteries, and 1 battery. But there's no real difference. We're just going to use all of these interchangeably because that's what we're going to do. And so that's the symbol for potential difference, or a battery. Anything that's a resistor, we're not going to draw like a toaster. That's just silly, right? Not that this symbol is that much different. It looks like Charlie Brown's t-shirt. It's a series of straight squiggle lines, and it's important that they are straight lines. They are not curly cues. That's something different. That's outside the scope of our course. So that's a symbol for a resistor. Why do we do that? Because we tend to use a lot of resistors in circuits, and this is just simple to draw. So if I was to draw this in terms of using these symbols, it would look like this. I would have, say, the positive plate there, the negative plate there. I'd have a wire, and I might go, if I'm just trying to make it look like what I had over there. Now, there it is. Now, we want to label a couple of these. We will label this R. If I had multiple resistors, I'd label them R1, R2, R3, R4, right? I always label the terminals of the battery or of the voltage source. I always label it with a delta VT, and we will say delta VT stands for the terminal voltage, not the total voltage, although oftentimes those are identical. Terminal voltage. And essentially the way that I want you to think about this is the source voltage provided. All right. The last thing I want to do here is I want to label the flow of charge. Well, we know that electrons are the mobile unit of charge. So there's an electric field set up around this wire from positive to negative, meaning the electrons here all start moving around this thing in a counterclockwise fashion, since electrons go opposite the direction of the electric field, right? Or if you want to think about this, you're trying to get away from the negative terminal towards the positive. Remember, then work is being done inside to move them from here to here, and they go on their journey. I'm going to label that with an I. Now, specifically, I might label a current here IT, and that would just simply be the current through the battery. Now, we'll talk about that a little bit later. These symbols, folks, are something called schematic diagram symbols. So if I ask you to draw a schematic diagram, I'm looking for something that looks like this. Now, another popular thing that we could put into a circuit that you have direct experience with is a switch, right? A switch is just something that opens or closes a circuit. And the symbol for a switch is just super obvious in a lot of ways. It looks like that. That's an open switch. That's a closed switch. And so if I wanted a closed switch in the circuit, I could just put in two things and I label with an S, right? Because that's what we do there. All right. So I just wanted to get those schematic diagrams out of the way, just because to be literate in the language of electronics, you need to know what these things look like. All right, cool. But our mission here is to quantify things. So let's start by talking about this notion of current. Now, descriptively, what is current? It is just the flow of charge. And we talked about a flow of, that we know we're talking about a flow of negative charge of electrons, because that's what's actually flowing. But historically, you should know that for centuries, when we had electrical currents, people thought they were positive things flowing, right? Back when this idea was invented, they thought that electricity was like a fluid, a positive fluid that went from one place to another. And that notion of a positive flow of charge would be something that's known as conventional charge, a conventional current. And that's actually what engineers today talk about, is conventional current. We as physicists talk about a flow of electrons, because that's actually what's happening. Not that I have a bias. But here's the thing about it. It doesn't actually matter, because a flow of electrons like this is the same thing as a flow of hypothetical positive particles in that direction. So mathematically, it works out to be the same thing. We'll talk a little bit later about what's actually happening on the atomic level that allows us to do that equivalency. But this definition doesn't tell me anything about how to quantify the notion of what is current. So if I asked you to quantify a water current, how would you do that? Now, it would be very tempting to say how fast the water is flowing. So I'm going to write that in red because it's wrong. Right? Or how fast the electrons are moving. Here's the problem with that. How many electrons do you think are flowing? And if you said to yourself a lot, you're right. If you said to yourself millions, you're wrong. If you said to yourself billions, you're wrong. Moles upon moles, like a billion times a billion times a billion electrons are actually flowing with even the smallest current. So it makes no sense to talk about how fast the electrons are going, because they're not all going at the same speed. They are on average going at an average speed, and stuff is getting in their way, so it's a lot more complicated. So we don't want to talk about how fast the water is flowing, because that's actually not even what they do with a river. If you put a leaf in a river and see how long it takes to go down, that's how fast the top surface of the water is going, not how fast the bottom surface is going, right? If you've ever been in a river, you know that at different depths, a current is flowing at different speeds, and that can actually be very dangerous. For example, that's why they tell you never to stand up in a river, because the surface is going a lot quicker than the bottom is, and that could force you to tip over, especially if your foot gets trapped. Anyway, I'm getting way out of bounds here, but still. Life advice, don't stand up in a flowing river. So, how are we going to do that? Well, actually, the way that you measure water current is you look at how much water passes a certain point in a river per unit time. So if you think about a slice of the river, and I'm seeing how many gallons of water go through that slice in a given amount of time, and that's what you do. It's something called a volume flow rate. We kind of do the same thing for current, but let me give you another example. Cars going down a highway, right? Going through a toll plaza. So what would be current there? Current would not be the speed of the cars. It's the number of cars that pass a certain point per unit time, because that's actually all that the governor cares about, because that determines how many tolls that they're collecting. The new speed lanes, you could go very fast and they can be quite narrow, right? But still get a lot of cars through because everyone's going fast. But the old toll lanes where you have to break up into the lanes, you have to talk to the person, blah, 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 right? What do they do there? Well, they widen the plaza so that they could have a lot of lanes, and so you have still a lot of cars going through, but they're all going through really slowly. New York State doesn't care if you're going fast or slow. They care about the number of tolls they collect, so the number of cars per unit time. Current is the same way. Current is going to be defined as the rate at which charge flows, which is deceptive, but measured as the charge that passes through one point in a circuit per unit time. And so here we go. I is equal to the rate at which charge flows. It's actually delta Q over delta T. Delta Q would be the change in the charge, right? The amount of charge that flows past in a certain amount of time. We tend to not use the deltas and we just go Q over T just for shorthand. So therefore, what are the units of current? Well, the units of current then are the units of charge, which are the coulomb, for the unit of time, which is the second. And a coulomb per second comes up so often in physics, it's given its own name, and that is something that's called the ampere, which we shorten to the amp, or as we were just going to write it, capital A. So 1 coulomb per second is equal or defined as 1 amp. There we go. So there you have it. So amp, named after Henri Ampère, a French physicist of the 19th century. Actually, when Ampère did it, he didn't actually measure it in this way. If you read Ampère's notes, the way that he measured current was he just literally touched two ends of a wire and said, ow, or like, ow, or then would use, French expletives. He actually had a relative scale of pain, and that was his way of measuring current. Henri Ampère's assistant would often find him passed out in his lab, not from imbibing, but from electrocution, which is kind of fun, I guess. But there you go. That's how we measure the notion of current. Now, what determines how much current flows? Well, amount of charge that flows per unit time. Well, let's get back to this. We know that this potential difference, well, what is that? So let's talk about the potential difference. Potential difference. Potential difference is defined as, right, the work done per unit charge. I will remind you, delta V, right? And that the units of delta V are the units of V, which are volts, after Alessandro Volta, which is a joule per coulomb of charge. So what does that mean? Well, remember what we said in the last video. Wherever there's a potential difference between 2 points in space, there is an electric field between those 2 points. So what happens here is the potential difference sets up an electric field through the conductor. And we know by our equation that the electric field is the same thing as the potential gradient, that the stronger the potential difference, or excuse me, the bigger the potential difference, the bigger in difference in charge concentration, the stronger the electric field. Now, if you think about that, we said that where was the source of charges that were flowing? Those were in the wires themselves. And so what happens is there's an electric field set up through the wires. Hopefully this makes sense, that if there is a field through the wires, and so electrons in the wire experiencing the field, if the field is strong enough, it's going to rip them off the atoms and force them to flow. The stronger the field, the stronger the force, the more charge that flows. That's our logic. So stronger field, right, is because there's a stronger, actually it should be stronger, let's try that again, sorry folks. Larger potential difference, right? Like I pick up a 6-volt battery or a 9-volt battery versus a AAA battery, which is 1.5 volts. Larger potential difference means a stronger electric field. A stronger electric field means a greater force on electrons in the wire. And that's going to mean more electrons forced to flow, right? They're ripped off of that. So since I is Q per T, if I have more charges flowing, that means my Q is going to be larger. So I'm going to say that the current is directly proportional then to the potential difference that the source supplies. Remember the terminal voltage. Okay, so that's the first thing. Now, the next thing is, you can imagine that those charges don't naturally want to flow. They have to be forced there. That those charges are going to be kind of stuck to their atoms in a particular way. And that's actually where the term resistor comes from. So we're going to talk about a concept that is called resistance, capital R. It is a quantification of the degree to which an object makes it difficult for charge to begin flowing. Now, notice there I don't say as it flows. That's not the way we're going to think about resistance. Resistance is a number that predicts whether the charge will flow or not what's happening to it as it's flowing. We'll get back to that later, right? And I think that makes sense, that different atoms will give up their charges to a different degree. In fact, we're going to say that there are 4 factors that affect resistance. Okay? And so these would be factors that the larger they are, the less charge that flows. Oh, by the way, what sort of relationship does that seem to suggest? Well, hopefully you understand that whatever this thing is, however it's measured, and we'll talk about that later, has an inverse relationship with the amount of current that flows, because its very definition is about how much charge is allowed to flow. The higher the resistance of the object, the less charge that flows. The first, I think, and most obvious factor that affects resistance is materials. So there is a distinction between copper and wood. Copper allows charges to flow very easily, wood does not. And so here's a really terrible word, but we're going to use it anyway, because there is a constant known as resistivity, which is different than resistance. Resistivity is a constant for a material. That suggests how strongly the object holds on to its electrons. Not the object, the material holds on to its electrons. And if you're thinking to yourself, hold on a second, in chemistry we have a word for that. That word is electronegativity. Here's the problem. The people who were studying chemistry and electronegativity were different than the people who were studying circuits, and they came up with parallel notions separate from each other. And so each discipline has its own way of talking about these things. Resistivity has the letter rho as its symbol, R-H-O. Look, the funny P. And hopefully what you would understand is metals have a low resistivity and non-metals have a high resistivity, right? And so the type of material determines the resistivity, but that's not enough. So now we need to talk about what's happening here. So now we have to talk about what current looks like. Current is a flow of electrons through the medium. But like when I talk about this wire, this metal wire, what is it actually flowing through? Well, it's flowing through the atoms of the material. And the way that solids are constructed is in what are called crystal lattices. The atoms of the nuclei of the substances are in this very definite rigid shape. Here I drew what would be a cubic crystal lattice, because you got to imagine a third dimension on this. And so what's happening here is an electric field. Actually, let's say the electric field is this way, so the charge of the flow of electrons is this way, that way. An electron gets ripped off, right? And so here's an electron moving along, boom, boom, there's my electron, and it's going down. So let's say this is an electron that's already been ripped off. But here's the thing, there are tons of these electrons, and the scale on this is wildly wrong, folks. Technically, the electrons are so much smaller than the nuclei. But here we go. And these electrons are all trying to make their way through. Okay. So let's talk about factors that would affect the degree to which the electrons make it through. Now, I'm also suggesting that these are all moving in straight lines. They're not. They're kind of like they're all moving kind of chaotically, because you got to remember the electrons are repelling each other. But what you'll notice here is this electron is going to get so close to this atom that it would kind of get like pulled into it. And that one's going to kind of like get through. But these electrons start messing with each other's paths, so their paths are kind of erratic, right? And so what happens is if a given electron gets too close to one of the atoms, it stops flowing. Or you can kind of think of it as just never flowed in the first place, because there's not enough space for it to flow. And so the actual physical spacing then matters. And here's two reasons, or two things. Have you ever played the game where you try and walk down the hallway, and the further you, without like bumping into anyone? Have you ever noticed that the further you have to go, the harder that is? It's the same thing for electrons. The further the electron has to go, the more likely it is to get pulled onto an atom because of its erratic path. And so we're going to say the next factor that affects resistance is the length of the path, such that the resistance is directly proportional to the length of the path, because the longer the path is, the more likely it is for the electron to get pulled back in. The next thing is going to be the cross-sectional area. All right. And so here's the thing. If I have a smaller cross-sectional area and the same amount of charges trying to flow, what ends up happening is the charges all get compacted. The electrons all get compacted. The crystal lattice doesn't get compacted, but if I have the same number of electrons trying to flow through, and there's less space, there's going to be more of them that are going to intersect with a given atom, right? And then stop flowing. And so the smaller the area, the more compact, the fewer, charges are going to be able to flow freely through it. You can also think about it in terms of water in a pipe. What's easier, for water to flow through a thick pipe or a thin pipe? It's a thick pipe, right? And so since it's harder to go through a thin pipe, the smaller the area, the higher the resistance, and that's what we have there. And so we can combine those three factors into an equation, rho L over A, and these are the factors that affect the resistance of an object. Notice they are all physical, right? Every given object has a length, a cross-sectional area, and it's made out of material. Boom, there you go. There's a fourth factor that affects this, and the fourth factor is temperature. Okay, and so I'll rely then on two things. One, your knowledge of your electronics, and two, we'll go to an analogy. When's it easier to, have you ever noticed that you run something really long and it heats up and then it takes forever to charge your phone or whatnot? Yeah, that's because higher temperatures mean more resistance. Now that's not going to be in this equation. It's a separate, more complicated equation, but it is a direct relationship. So now we're gonna have to talk about this at the atomic level. What's temperature? Hopefully you remember, for temperature is the average a measure of the average kinetic energy of the molecules of a substance, right? So it's about how fast things are moving. Now here's the thing. It's not about how fast the electrons are going. It's about these objects, these nuclei. Now, you might be saying to yourself, Vaughn, you said that those things are locked into a rigid crystal structure. And I did, but that doesn't mean that they don't vibrate. Everything at the atomic level vibrates in some description. The higher the temperature, the more they vibrate. So can you imagine, at a low temperature, the vibration is very small, very easy for the electrons to get through. At a higher temperature, they're vibrating, they're gonna block a lot more of those charges, which is why higher temperatures mean a higher resistance. So, I know that was a lot. But then, to bring it back, we said that the amount of current that begins flowing is directly proportional to the potential difference of the source. Let me write that again, because that's terrible. Okay, I don't know why I did that again. And we said that the current was inversely proportional to the resistance, and there was a bunch of things that were in here. But we're gonna combine these two and then into an equation. I'll tell you that the proportional constant is 1, because it's actually the resistivity, which is baked into the resistance factor, and there we go. So that's what we have. That the current that begins to flow is equal to the ratio of the total voltage over the terminal voltage over the total resistance. So I will put an RT there, and I'm gonna put an IT there. The current through the battery is the ratio of the terminal voltage over the total resistance experienced. There you go. This is something that's called Ohm's law, after Georg Ohm. And that is the reason why the unit of resistance is the ohm. The symbol for an ohm can't be a 0, because that would be problematic. It is the Greek capital letter omega. So what's an ohm? If you look at this equation, an ohm is a volt per amp. So that says for every volt of potential difference, I get a 1 amp of current through that for a 1 ohm resistor. And so there you go. Ohm's law is our first and major equation for quantifying what's going on in a circuit. Greater potential difference, more charge flows. Greater resistance, because one of those factors is bigger, less charge flows. And so next week we're going to look at a couple more equations, as well as a little bit of a deeper notion of what's going on inside or for a circuit, but I think that is probably enough for today.